our first question is that Kyle is investigating the heights and the weights of professional basketball players. He found that the weight in kilograms of some professional basketball players from 1950 to 1959. They want us for question A to circle the word from the list below that best describes weight in kilograms as a type of data. Here, weight in kilograms would be continuous data. That would be your first mark. We have then been given an incomplete histogram and an incomplete grouped frequency table to give information about the weights. Here we need to, for part B, complete the table. So in our histogram, from the information we've been given, we can tell that every 10 squares is worth 20, so therefore every 1 square is worth 2. This tells me that my group from 85 to 90 is going to be 80, 2, 4, 6, and then one more, so it'll be 87. My group from 90 to 95, that's going to be 20, 40, 2, 4, 5, so it will be 45. We then, for part C, need to complete our histogram. The groups that are missing is from 95 to 100 and then 100 to 105. So for 95 to 100 we've got 35, so we're going to have 20 and then we're going to have 2, 4, 6, 8, 10, that's 30, 2, 4, 5. That mark is going to be 35. We then need to use a ruler and hopefully a pencil as well to complete our bar. Then for our next one we've got 14, so we're going to have to count up 1, 2, 3, 4, 5, 6, 7 up, and again using our ruler and hopefully a pencil we are going to complete our bar. We then have for part D that Kyle also drew a histogram for the weights of professional basketball players from 2000 to 2009. All we know about this histogram is that it is negatively skewed, so we need to use this information to interpret the negative skew. Here you essentially needed to say that the tail of the data is left, and what we mean by that is the weight of the basketball players below the median is more spread apart than the weight of the basketball players above the median. You could have also said the mean of the basketball players' weight is lower than the median, or you could have also said more than half of the basketball players weigh more than the mean. Any of these points would have got you that 1 mark. So we also have that Kyle collected data about the heights. So he collected data about the heights from 1950 to 1959. He also collected data from the heights from 2000 and 2009. Here we've got a grouped frequency table, and it gives us information about the heights from 2000 to 2009. Part E wants us to estimate the mean height. We've been given the mean height from 1950 to 1959. We've been given that that is 190.9 centimeters. So we just need to use our table from 2000 to 2009 to estimate the mean height of the basketball players from 2000 to 2009. Because it's an estimate here, and because we've only got grouped frequency, we need to use the midpoint of our groups. So our midpoints would be 175, 185, 195, 205, 215, and 225. Now we have these midpoints, we can multiply the frequency and the midpoint together. So here we can do our frequency multiplied by our midpoint. When you do this, you should get the value 2,100, 27,010, 34,125, 66,215, 31,390, and 1,800. Now, if you sum these all together, you should get 162,640. In order to find your estimated mean, then, the calculation we need to do is your frequency multiplied by your midpoint, your 162,640, divided by your total frequency, which was 810. Doing that will get you 200.790. I'm going to round that to one decimal place as we've done here. It's not said what we need to do in the question, so that would be 200.8 centimeters. Here you would get a mark for doing your frequency and your midpoint, multiplying that together. You would get a mark for showing your calculation of your estimated mean, and then you would get 1 mark for your answer. We're then being asked to comment on how the mean height has changed between the two data sets. So from 1950 to 1959, it was 190.9 centimeters. Then to 2000 and 2009, it was 200.8 centimeters. So what we needed to say here is the mean height of basketball players has increased, and that would get you that mark. For question 4, we have that we are investigating the performance of athletes in long jump. To do this, we are finding the height of how the height of an athlete affects the distance jumped. So we are looking at plans to collect, process, and present this data. The details we've been given have been split into 2 categories. It's been split into collecting data, and it's been split into processing and presenting data. Because it's been split into collecting data and processing and presenting data, in our answer we do need to make sure we are mentioning both. So our question is to discuss the plans for collecting, processing and presenting data and see whether they are appropriate. Starting with points we could have made specifically about collecting data, it is a suitable sample size, we could say that. We could also say that some students may not agree to take part, or there may be absent students. We could also mention that asking students to measure their own data might lead to inaccurate results. Also, only jumping once might not lead to accurate results, so we could mention that students should jump more than once, and we could use the mean from their jumps. In terms of points we could have raised about processing and presenting data, we could say that scattergrams are more appropriate for height and distance jumps. We could say, though, that the height should be the horizontal axis. This is because the height is the independent variable, and distance jump should be the vertical axis because that would be our explanatory variable. We are choosing to look at it with height, but age could also affect results, so therefore we could mention that. We could also say that a line of best fit on our scatter diagram would be appropriate as long as there is a correlation visible. If there is no correlation, this wouldn't be helpful to us. This question is worth 5 marks. That tells me I need to have written down at least 5 points. But you have to try and split them equally. So you could only get 3 marks if you only mentioned points about collecting data. So you could get max 3 marks just from data, collecting data. and you could get max 3 marks from just mentioning processing and presenting data. If you've mentioned points from both, then that's when you're going to get your 5 marks, as long as we've written down at least 5 points and they are weighted equally between the 2 categories. For question 6, we have that the table gives information about monthly average price per troy ounce in pounds of gold over a 6-month period. So we've got a monthly average over a 6-month period. The table has given us some of the chain base index numbers. These are correct to 1 decimal place. So we are looking at our chain base index. For part A, we have been asked to calculate the chain base index for June, and we want to write it in the table. Our answer should be correct to 1 decimal place. So in order to calculate the chain base index number for June, we need to take our monthly average price from June and divide it by our monthly average price from the month before, which was May. So we need to do divided by 1000.0. We then need to multiply by 100. That is going to give me 107.19. It wants it to 1 decimal place, so in my table I'm going to write 107.2. You would get a method mark for writing out this calculation, and you would get a method mark for your answer. So part B is asking us to calculate the geometric mean of the 5 chain base index numbers that we have got. We must show our working, and it's got to again be correct to 1 decimal place. For our geometric mean, we've got 5 numbers, so we are going to do to the power of 5 square root, and here we are going to write 101.3, that's our Feb chain base index, multiplied by our March chain base index, multiplied by our April, multiplied by our May, multiplied by the one we've just found, our June. And when we type that into our calculator, we are going to get 101.3695747. Correct to 1 decimal place is going to be 101.4. Here again, we've got that split where we're going to get 1 mark for our correct writing of workings, and then we're going to get 1 mark for our correctly rounded answer. We have then been asked to interpret our answer in context. So here we've got 101.4, 101.4. What we can say about that then is our average rate of increase per month is 1.4%. Here are important things to have mentioned was about it being an increase, that it's per month, and that it's 1.4%. We needed to have mentioned those things in order to have got the 2 marks. If you had mentioned that it was just an average rate of increase of 1.4%, that would be 1 mark. The 1.4% did need to be put in this question to get a mark. For question 8, we have that Ian collects information about whether drivers have had advanced driver training and whether they've exceeded the speed limit in the last month. All the information in this paragraph has been put onto our probability tree diagram. The only information that we are missing that we need to put on is that for drivers who have not had advanced driver training, 26% of them have exceeded the speed limit in the last month. This is going to then help us for part A to complete the probability tree diagram with this information. What this tells me is if they are not an advanced driver, they've exceeded the speed limit, that probability there was 26%. So that as a decimal will be 0.26. We can find this answer here because these two will need to sum to 1. So if we did 1 subtract 0.18, that's going to give me 0.82. Very similar down here, we need to do 1 subtract 0.26, and that will give me 0.74. So that is my completed probability tree diagram. You needed to get all of those correct in order to get that 1 mark. For part B, we've been asked to calculate the probability that we've got an advanced driver on the condition that they've not exceeded the speed limit. Here, just for ease, I'm going to call this AD for advanced driver and NESL for not exceeded speed limit, just so we're not writing it out over and over. The calculation we're going to need to do is the probability that they are an advanced driver and they did not exceed the speed limit, and we need to divide that by the probability of not exceeding the speed limit. I want us to start by just looking at the probability that they are an advanced driver and they did not exceed the speed limit. What we mean there is they were an advanced driver, did not exceed the speed limit. So our calculation there is that we are going to times, we're going to times as we move down our probability tree. So we are doing 0.18 times 0.84. That's going to give me 0.1512. So my probability that they are an advanced driver and they didn't exceed the speed limit is 0.1512. Then we'll look in general about the probability that they did not exceed the speed limit. Now there's 2 routes to get to not exceeding. We've already calculated the probability of that first route. The first route is that they're an advanced driver and they didn't exceed the speed limit. The other route is that they were not an advanced driver and they did not exceed the speed limit. So this one here, to calculate this, again we're timesing as we go down our probability tree, is going to be 0.82 multiplied by 0.74. That, if I type that into my calculator, will give me 0.6068. So in order to get my total probability that we didn't exceed the speed limit, we then need to add those 2 probabilities together. So we need to do 0.1512 plus 0.6068. When I add those together, I should get my result to be 0.758. I now have my 2 probabilities and I can calculate my probability that I'm trying to find in part B. So I'm going to do 0.1512 divided by 0.758. That is going to get me 0.199472 and so on. I'm going to round this to 3 decimal places, so I'm going to round that to 0.199 for my final answer. Here, you needed to have calculated both of those probabilities to get 1 mark. Then your final answer will get you that 2nd mark. For part C, we want to calculate the relative risk of exceeding the speed limit for the non-advanced drivers compared to the advanced drivers. So looking at that non-advanced drivers, that's 0.26. In order to compare it to the advanced drivers, the exceeding speed limit is 0.16. So we're going to divide here. That's going to get me 1.625. So my answer here, my relative risk, was 1.625. Here you'll get 1 mark. For your calculation, you're going to get 1 mark for your answer. So part CII was interpret this relative risk in context. So what we needed to have said here is that the risk of a driver who has not had advanced training breaking the speed limit is 1.625 or 162.5% of the risk of a driver who has had advanced training breaking the speed limit. If you didn't want to say it was 162.5% of the risk, you could have said that it was 62.5% more than the risk, and that would have been okay. We then have that Ian researches the relative risk of exceeding the speed limit for newly qualified drivers compared to those who are not newly qualified. He finds that in 2019 the relative risk was 0.95 and in 2020 the relative risk was 0.85. Ian concludes that the proportion of newly qualified drivers exceeding the speed limit, so that's newly qualified drivers exceeding the speed limit, has decreased between 2019 and 2020. Part D is asking, do the statistics support Ian's conclusion? Here what we should have said is no, it's not possible to tell. This is because it could be that the proportion of newly qualified drivers has reduced, or it could be that the proportion of not newly qualified drivers speeding has increased. So those are two different options that you could have had. But here it was important to say, no, it's not possible to tell, and then you justify it with a reason why. Here as well, sorry, it should be that the proportion of newly qualified drivers speeding has reduced. For question 10, we have that a study took place in the southeastern United States to find if there was a relationship between snout vent length in centimeters and body weight in grams of adult snakes. The researchers found the equation of the regression lines for the relationship between snout vent length, which they called x centimeters, so our snout vent is our x, and body weight, which is y grams, so body weight is going to be y, for each species of snake. They looked at two species. They looked at timber rattlesnake and they looked at eastern racer. There was a difference in the relationship between the two variables for female snakes and for male snakes as well. For easing this question, I'm going to call timber rattlesnakes as TR and then eastern racer as ER. Part A is asking us to interpret in context the figure 19.61 in the regression equation for the female snakes for timber rattlesnakes. So here what they're essentially meaning is this 19.61 and this 19.61. They want us to tell them in context what that means. What that does mean is that as snout vent length increases by 1 centimeter, the weight increases by 19.61 grams. For part B, they've asked us to compare the relationship between snout vent length and body weight in the two species of snake. So we need to compare between the two species, but we also need to include a comparison between male snakes and female snakes. So starting by looking at all snakes, we can see from our regressions that the weight increases as snout vent length increases. So that's happening across all snakes. For a male-female comparison, we can say that the male snake's weight increases faster with increasing snout vent length. And then for species, we can say that our timber rattlesnake weight increases faster than our eastern racer weight when considering our weight in comparison to our snout vent length. So as our snout vent length is increasing by the same amount, the timber rattlesnake weight is increasing faster than the eastern racer snake. Here, for the male-female, you could have compared your male and female timber rattlesnakes, or you could have also compared your male and female eastern racer snakes, or you could have compared them all together, as I've written down here. Same thing when we're looking at our species. You could compare the male species separately and the female species separately as well. Those would be considered appropriate. So 3 points considering male-female relationships and our species relationships and differences. That will get you those 3 marks. We are then told that the researcher would like to use a normal distribution as a model for the weights of the male timber rattlesnakes. They plan to draw a histogram to calculate the averages and standard deviation for these weights to check whether a normal distribution is a suitable model. We've been asked to then explain how they could use a histogram to check whether a normal distribution is a suitable model. Here, if we drew a histogram, this would help us because it would allow us to see whether a bell-shaped distribution is apparent. So we need to use a histogram to allow us to check for a bell shape to the distribution. Then for our next part, we've been asked to explain how we can use the averages and the standard deviation to check for whether the normal distribution is a suitable model. Just for ease, I've just abbreviated standard deviation to be S.D. So one point we could make is we could check the mean, median and mode are equal. That would get us 1 mark. We would have to say one of the points, we couldn't say all 3 points, but we'd have to say one of the points here in order to get a mark. We could check that 68% of the data is within 1 standard deviation of the mean. We could check that 95% of the data is within 2 standard deviations of the mean. Or we could have said that we could check that almost all the data is within 3 standard deviations of the mean. Now here, if you put these 3 points, you would get maximum 1 mark. One of these points would give you a mark. Another point you could have said is we could use the mean, median and standard deviation to calculate skewness, and that would help us see whether a normal distribution is appropriate. So you can get 2 marks here. You could get a mark for a point from each of these categories.